Okay, what are your questions about today's reading, yesterday's?
Can we go over oxidative cleavage in an acid versus a base?
So oxidative cleavage of the double bond or the triple bond?
The triple.
The triple bond. Okay, so if you have a triple bond, our oxidative cleavage is going to cleave, we're going to end up cleaving the triple bond, and unlike with the alkenes, when you oxidatively cleave an alkene, you can end up with ketones, aldehydes, or carboxylic acids. A triple bond is going to be much harder to cleave, and so you're going to have to use a much stronger reagent in order to cleave it. And when you do, you're going to end up with having no choice but to form the two carboxylic acids. So when you cleave the double bond, or when you cleave the triple bond here, you're going to basically have those two fragments. And then you're going to add in the oxygen. And since this is a primary carbon, your only choice is aldehydes or carboxylic acids. Since the reagent has to be strong, it's going to end up with two carboxylic acids. So the stronger of the two reagents is KMNO4, acid, and probably heat. Although I think, let's see, there's also a sort of a tetrahydroxyl compound that will end up forming a diketone. I don't think that's in the book, but I think that might be in my notes. So are you talking about forming the two ketones versus when you cleave it? Or just cleaving the double bond?
Yeah, the triple bond.
Okay, or cleaving the triple bond. So I think as long as you apply heat, you're going to cleave it. So whether it's hydroxide and heat or H plus and heat and KMNO4, you're going to end up cleaving the triple bond. You can also use ozone for this. And so you could use ozone, which is O3, and H2O2 goes with that. So you could end up using ozone to do the cleavage as well. So the difference between using acid and base is really only going to be in the final product. Because if you cleave this apart and form a carboxylic acid, in the presence of acid, it's going to stay. But if you were to cleave it apart and make the carboxylic acid in the presence of base ends up deprotonating the carboxylic acid. So the product that you make is actually a deprotonated carboxylic acid. So you end up forming two carboxylates that then you would have to add H plus to in order to get them to go to form a carboxylic acid. So if you use a strong acid, this is just, you form these two products. It's only if you have a carboxylic acid and base is when the base deprotonates the carboxylic acid and it makes the carboxylate. And then if you want to form the carboxylic acid, you have to add some acid to that in order to make the carboxylic acid. So the difference would be a small one. If you use basic conditions, it'll be a carboxylate. If you use acid conditions, it'll just be the acid right away. You won't have to take the second step. But either way, ozone and peroxide, or either one of acid and base, with heat, and I think heat is the key part, and KMNO4 will cleave the double bond. Or the triple bond. It'll cleave the double bond as well. But the rules are a little bit different there.
Can you go over the products when it's a terminal or internal and then symmetrical and symmetrical alkyne?
With what reagents?
With the hydration.
Okay. So, terminology is that if you have the hydrogen at the end, that's a terminal. That's a terminal alkyne. If you have two alkyl groups, that's an internal alkyne. One of the things with the internal alkyne is that we usually make those symmetrical. So, for instance, if I was going to use an internal alkyne for any of the reactions, I'm probably going to make it symmetrical by making the two alkyl groups attached to the triple bond the same. And I'll show you why that is. So if we're going to do hydration, remember hydration is acid and water. Now, sometimes you will see mercury, a mercury 2+ ion as a catalyst, and all this does is that the mercury, well, remember how the mercury kind of sat on top of the double bond when we did mercuration, demercuration the other day? The mercury isn't going to play a role in the final product, but what it does is it can activate the triple bond so that it reacts easier with the acid and the water. So that's why we use mercury, is just as kind of a catalyst to make the reaction go faster. Whether you include the mercury or not is irrelevant. So I'm going to add my H plus to this internal alkyne. So I'm going to take and add it. Doesn't matter which carbon of the triple bond I add it to. No, because this is a symmetrical alkyne. So I'm going to get the same product whether I add the H to the left carbon or the right carbon. So I'm going to add the H plus there, and then that's going to add that carbon there, make a double bond, and then I'm going to end up with a plus charge on the other carbon. So all I'm doing is the same first step in the addition that I do with the double bond, except with a triple bond, there's now a plus charge attached to the carbon that's in the double bond. So then my water's going to come in, and the water's going to add to the carbocation. To make the oxonium ion, bless you. To make the oxonium ion. And remember, you've got to add the whole water molecule. You can't break it up. And so then I'm going to lose my H plus to then form the final product, the almost final product. And that's called the enol because it's half alkene, half alcohol. So, first thing is, if this was unsymmetrical, if there was a methyl group on the left side and an ethyl group on the right-hand side, we would end up with two different enols. Which means when this undergoes its tautomerization, I'm going to end up with two different ketones. So any reaction we do with an unsymmetrical alkene or alkyne is going to give both products, because since it's an alkyne and since it's internal, Markovnikov's rule is going to be that you add to the carbon in the triple bond with the most hydrogens. Well, they're always going to be tied if there's two alkyl groups attached to it. So that's why we make it symmetrical, just to get one product. But if it was unsymmetrical, you would get a 50-50 mixture of the two products. Okay. So we're going to make this enol. And you might say, well, are the two methyl groups going to be cis or two methyl groups going to be trans? It's actually going to be 50-50. Because this carbocation, the water is going to attack the carbocation on both sides. So the stereochemistry here is not important, because we're going to get a mixture of cis and trans. And it won't matter for this enol, because enols are unstable. So just rewriting that, and I'm going to write the OH group. I'm going to write the OH like that. So this enol then undergoes an equilibrium reaction, which is called tautomerization. So it's going to tautomerize. So what tautomerization means is that I'm going to use a pair of electrons, or I'm going to move a pair of electrons and a hydrogen atom at the same time. So this is an equilibrium. It's not resonance, because resonance would mean that I can't break any bonds. I have to break bonds here while I'm moving my pair of electrons, so it's a tautomer as opposed to a resonance structure. And the way the electrons would move would be something like this. I'm going to move this pair of electrons here from the hydrogen, and then I'm going to move this pair of electrons out from the carbon, or from the carbon-carbon double bond. So what I'm going to end up doing is I'm going to end up having that hydrogen move from being bonded to the oxygen to being bonded to the carbon. And so I'm going to end up then with that that carbon now having the new hydrogen attached, and then the oxygen becomes a carbonyl. So this is called a Keto-Enol Tautomerism reaction. And for most ketones particularly that only have one carbonyl group on it, C double bond O group, for most ketones the keto form is far more stable. There are some other ketones, particularly if you have two carbonyls, where it turns out that the enol form is much more stable. And if you're a chem major and you end up taking something like physical chemistry and physical chemistry lab, there's a whole experiment on measuring the keto-enol equilibrium by NMR that we do here, and actually Dr. Weiner and I have published sort of a variation on it that we found by accident. So these are pretty classical reactions, but there's still a lot that's not known fundamentally about it. And I think in one of our papers, the person was like, "This is the resonance structure," and we had to point out to them gently, because they were refereeing it, it's a tautomerization, not a resonance structure. Just enough to make sure we knew what we were doing, but not enough to anger them so they would reject it. So if I took, for instance, and made an unsymmetrical alkyne, and said, let's react that with H plus H2O, what would be the two products of that, final products of that reaction? I'll give you a minute to write them. Should get out the little chalkboards. So write the two possible products on your little chalkboard. All them Okay, now turn those into the final product. So first you're going to form an enol, and then when you form the enol, you want to turn that enol into the final product. Okay, yours is okay. So you want to, I want both products. So I want both enols and both ketones. You got one. Okay, now turn those into ketones. Okay. I see carbons with 5 bonds. Better. Okay. Five bond. You got your ketone has 5 bonds to your carbon. Okay, those are the enols. Now turn them into the ketones. Okay. Okay, so when you're doing this, there is no Markovnikov addition, so you're going to get an unsymmetrical and you're going to have to put both products down. This is going to be the case for HBr addition, both Markovnikov and anti-Markovnikov. This would be the case if I tried to do this reaction anti-Markovnikov hydration, adding H and OH. So you're always going to get a 50-50 mixture of products. But what you want to do is you would say, okay, I'm going to add my H and my OH in opposite sort of directions on the molecule, so that this would be the enols, which many of you showed me. And then what I want to do is then I want to convert them to, then I want to convert those to the ketones. And so when I convert it to the ketone, I'm just going to basically convert the COH into a C double bond O, but remember that the hydrogen transfers over. So for instance here, this hydrogen is going to end up transferring over to that carbon, and this double bond is going to disappear. So if you're going to form the carbonyl, you can't have a double bond. You can't have the double bond still intact, the carbon-carbon double bond, right? Because that's going to give you 5 bonds. So this product, so the first enol is going to become that one, and then this enol is going to become, this is going to be a CH2, and then you're going to have the ketone, the carbonyl group in the center of the 5 carbon chain. Yeah. Which so it's a CH2. So you could write it as a CH2 if you wanted to. So, symmetrical alkynes, I will normally give you a symmetrical alkyne. I don't have to. If I do give you an unsymmetrical alkyne for any of these reactions, you're most likely going to get 2 products unless the reagent is symmetrical. So if you're adding 2 BRs, then it doesn't matter. You're only going to get 1 product. But if you're reacting an unsymmetrical reagent with an unsymmetrical alkyne, you're going to get both products 50-50. Now, what if I had a terminal alkyne? If I have a terminal alkyne, what am I going to do with that? Well, if I add H plus H2O to that, where's the hydrogen going to have to add? To the carbon with the most hydrogens, because it's going to be Markovnikov addition. So in this case, I'm going to, it doesn't. It only has a CH. It's a typo. How does it even have any H's? It doesn't. So for terminal 1, you're going to add the H. Yeah, this is all messed up. There. So you're going to add the hydrogen to the carbon with the most hydrogens and the OH to the other carbon. So you're going to add the H and OH to make the enol. So this one has to go by Markovnikov's rule, and then that enol is going to convert to the ketone. So the hydrogen from the OH is going to slide over. Double bond's going to basically form in the CO double bond. So this would be the major product, and probably only product that you would get if you use a terminal alkyne. So the terminal alkynes always give you Markovnikov products. And it's the same mechanism. And if you look back on some of the older exams, you'll see that I typically ask for, when we're in the alkyne reactions, I will typically ask this reaction to have you write the mechanism. So have you add the H plus to the triple bond, have you add the entire water to the carbocation, and then have you show the arrows of the Tautomerism. So that happens. No, so what happens is that the equilibrium lies mostly towards the ketone. Simple enols are like this is acetone that we made right here. The enol of acetone is very unstable. Although I seem to recall at one point somebody at the University of Toronto sent it to me to try and get an X-ray crystal structure to get the exact structure of it, and I couldn't. But I think within the last 20 years, they've finally isolated that enol. But that's how difficult it is because it's just so unstable. So simple ketones don't form very much enol. Which is why once you form the enol, immediately tautomerizes to form the ketone. So this is the product I'm going to be looking for, is the ketone. Now, if I can do Markovnikov addition, can I not do anti-Markovnikov addition? So could I, for this molecule, say, you know what, I want to take this, and I want to form not the ketone, but now I would like to add the H and the OH anti-Markovnikov, and then have this tautomerize to form the aldehyde, which is what a C double bond O with just an H attached to it is called an aldehyde. So what reagent would I use to do anti-Markovnikov addition of H and OH? So that's our hydroboration oxidation. So I can try and use that same reagent. So do we remember what the steps of this reaction were? I'm going to add the BH2 to one carbon and add an H to the other. So the way this is going to add is I'm going to end up with the BH2 and the H basically adding to the two carbons in the triple bond through a square transition state. Square transition states mean that those two groups add 100% cis. And why does the boron add to the carbon with the least amount of alkyl groups? Because there's a steric issue here. So that's why the boron added to the least hindered or least substituted carbon, was because of sterics. But here's the issue with alkynes. Alkynes are linear, and so there's not as much steric hindrance in a linear system as there is in a tetrahedral system. So this boron then is actually going to have a hard time discriminating between the terminal alkyne and the internal alkyne. This isn't going to be 100% addition to the terminal carbon if it's just BH2, because the BH2 is small enough where it could fit in either place relatively well. So what we do is we go back to our, sort of our toolbox that we have and say, okay, my reagent, my alkyne reagent isn't sterically hindered enough to differentiate between adding terminal and internal. So now let's go ahead and make the BH2 sterically hindered to force it to add to the outside. And so that's the approach that people use, is they take the boron and they now make it sterically hindered. And one of the reagents that they use is to use, I think, let's see. They use this, they attach this group to both and in what's not even close to being a legitimate common name. They call this isoamyl. Because it's a 5-carbon group, when amyl is the older term for pentyl. And it has an iso group, so they call it isoamyl. But again, that is not even close to being a correct IUPAC name, or even a close common name. But that's what they say. So this is actually, this is abbreviated as, I believe, SIABH. Somehow they make that. So this now is sterically hindered enough where it forces the boron to add to the terminal carbon. And so you can get that up to 100% yield. You have to use this at an equal molar ratio because the boron can only add 1 hydrogen, whereas over here the boron can add up to 3 hydrogens. So it's SiA2BH. Oh, because it's secondary isoamyl. That's what the S stands for. This is secondary isoamyl. Again, it's totally screwing up the common name system. So they sometimes call this SiABH. There's other reagents your book may have used, like 9-BBN. But they all have the same basic feature, which is if the triple bond isn't going to be sterically hindered enough to differentiate between adding terminal and internal, then let's use a sterically hindered reagent because that will. It's kind of like, why do we use a sterically hindered base to do E2? Because I want to cut down on that base's ability to be a good nucleophile and add and do substitution. So if we use that reagent, then we add the H-NeoH anti-Markovnikov and the anti-Markovnikov, then that OH at the end of the molecule now becomes an aldehyde. You have to know the mechanism for this, not this one. So that's a long answer to the hydrations. But that's the one reaction that is completely different with alkynes than with the alkenes. So usually when we start alkynes, I'll say, well, if you remember all your alkene reactions, you're in great shape. Because the difference between an alkyne and an alkene is I can do all the reactions of alkenes on alkynes twice, because I've got 2 pi bonds. If you don't know your reactions of alkenes, well, then that's a whole other story, because now you're missing 2 complete functional groups. And we can still classify these reactions as regio and stereoselective, only in this case the stereoselectivity would be whether you get 100% cis or 100% trans in the alkene product. What other topics did you have issues with? Okay. The other reactions that are different are the reductions to turn the triple bond into either a single or a double bond. That's a different set of reactions. It's a new set of reactions. So I have the full complement of reactions. I can take the triple bond all the way down to a single bond, and I can also form the cis and the trans alkenes depending on which one I want. So the question is, which reagent goes with which set of reactions? So let's do this. So let's break up into groups here and do these three, and then then I'll just continue to do problems. So let's see, I've got Brandon and Kaylee, and Eleanor and Megan. Eleanor, Megan, Brandon, Kaylee, Greg, Hannah, and Mel, and then Aria, Max, and Cameron. So you can just kind of rearrange yourself to be.
So which reagents did you use to do? If you have notes from the reading and or the video, that would be helpful. Because then you can choose which one you need. So then the middle so here the only way back to here you stop so it's like this
the special catalyst.
Yeah, I know, but that's not going to be a influence. You got to know what its name is. So we'll do it in chapter number.
Okay, so then So then, if you have that, so then if you have the reductions done, my next question is going to be, you're going to have to take more than one reaction, but how would you add them? How would you take the triple bond from that molecule without the CH3 here? So you got to figure out what you're adding and then how you're going to add those four. You're going to add 4 groups to that, or 4 atoms. So you got to figure out how to add them in groups. There's more than one way to do this. So now the question is, you're going to do more than one reaction. You're going to add 2 BRs and 2 Fs. But we've got a couple of reactions to get from there. So what reaction is
Because I don't have the same time
There's a couple of ways to do this sequence. There's more than one way to do it. So if you're like, well, we could do this or we could do that, that's true.
You could do both.
Okay, so you have a few. So you have the first one. You got that. That line. And then you have the second one. Okay, so how do you have so you had it.
Oh, so this one made. Oh, yeah, so then you can just
This makes sense.
Quick. Matter exactly what you got back or which two is to be happy at? This would be the first, this would be the second, and this would be the first, this would be So if you want to make that, you got
So, because I had it in so, so then it's not.
So you got change your reaction to alcohol. So then you have to say what you want to do.
Wait, so what did it have that
So if you want to go from here, then you have another way to do it. Alcohol, but alcohol, so that's one way.
Let me break this out.
That's one way. Another way. So the question is, you're adding, when you add So then the question is, how do I add those two ketones? And then how do I get them in the position that I want them?
Okay, first things first here. I kept recording that. Okay. So what we need to do is we need to, for the reductions, there's 3 different reductions, so you have to know these reagents. So you have to say, well, H2, palladium, or platinum metal will give me the alkane. Why does it give me the alkane? I wouldn't use unrestricted, but the palladium and platinum metal is reactive enough so that when the first set of hydrogen atoms add to the double bond, you form an alkene. Well, how do you take an alkene to an alkane? You use hydrogen and palladium. So the palladium and platinum metal is strong enough to where it's going to reduce all the way down to the alkane, because it will react with the triple bond. It'll also react with the double bond. So what we do is we use excess hydrogen gas and let it go. So the hydrogen gas would first react to form the carbon-carbon double bond, and then the second equivalent of hydrogen gas with your palladium and your platinum metal catalyst would then react with the double bond to go down to the single bond. I can't stop it because the palladium is just too reactive of a catalyst to stop at the alkene. You might say, okay, well, let's just add one equivalent stoichiometrically of hydrogen gas. Number one, that's not easy. Number two, some of the hydrogen's going to be used to form the alkene, and then some of it's going to be used to form the alkane. So I'm going to get a mixture of all three products. I'm just going to take it all the way down to the single bond. So if you want to go to the single bond, you use full strength palladium or platinum metal catalyst. You want to stop. I want to stop at the double bond. Well, first of all, if I stop at the double bond and I use a metal catalyst, it's going to add cis. No choice. It's going to add cis. So what do I do to the catalyst? I deactivate it, make it less reactive. There's a specific term for that. It starts with P. What? No? I'm going to deactivate the catalyst. So it's called poisoning the catalyst. So if I poison the catalyst, what's going to happen? It's not going to be able to reduce the double bond, so it's just going to stick at the double bond. So what do I use? Well, who poisoned the catalyst? Lindlar. What did he do? He used palladium, but then he added something like barium sulfate, and he added this molecule called quinoline to it. And so he made a poison catalyst that would stop at the double bond. Normally, catalysts get poisoned because impurities end up attaching to the surface and killing the reactivity. There's a lot of catalysts in the refining process where they take the crude oil and they end up converting it to gasoline or kerosene. And so a lot of those catalysts, the biggest problem is they get poisoned along the way, primarily by sulfur, because there's sulfur in the crude oil. And so you have to keep your catalyst from being poisoned. This is an example where Lindlar deliberately poisoned it to stop it at the alkene. And then if you want to form the trans alkene, you go with a completely different mechanism, which is sodium metal and liquid ammonia. And so the mechanism for this is outlined. It basically, when you put sodium metal in liquid ammonia, first of all, where do you get liquid ammonia? You have to make it, because ammonia is gas. So you basically take a round bottom flask and you put it in like dry ice with rubbing alcohol, that's -78. And then as you add the ammonia gas, it liquefies. And then you add a drop of sodium metal to it, and it turns this color blue. It turns a bright Duke blue instead of the other crappy blue. The light sky blue, which we don't like. We like the dark Duke blue. That's where I got my PhD, so. And had season tickets. So what happens is that the sodium gives up an electron. It gives up this free electron that runs around the solution. You cannot get a pure reduction reaction than to have a pure, unadulterated electron adding to something. And so that's what happens. And so that is specifically trans. So the hydrogens end up adding trans. So you have to know these three reactions in order to tell me which reagent would I use or which product do I get. So those are the three reductions. Then for this one, which isn't out of the realm of possibility for me to ask next week, say, hey, how many, take 2 steps and give me this product. So the first thing you need to do is to analyze, well, what am I adding? I'm adding 2 H's and 2 BRs. So there's 2 ways to do this. You could say, I'm going to take my alkene and I'm going to add HBr to it. How is the HBr going to add? I didn't. There. So alkene, what am I adding? H and a BR. How? It's either Markovnikov or anti-Markovnikov. Those are the 2 choices. Markovnikov, which means that the BR is going to add to the end or middle carbon, the middle one. Okay, so then I'd say, well, let me add a second equivalent of HBr. Except if I add HBr to this one, what am I going to end up with? 2BR, and that's not what I asked for. So I still need to add HBr, but how do I need to add it this time? Anti-Markovnikov, which means I have to remember what do I add to HBr to get it to add anti-Markovnikov? Peroxide. So then if I add peroxide, it'll go anti-Markovnikov. Now, which carbon has the most hydrogens? The one on the end. What does that get in an anti-Markovnikov reaction? It gets the BR, it doesn't get the H. So in this case, I'd have my CH3 with my carbon, my H adding here, and then over here, 2 H's and a BR.
For the first one, use H2O2 and H2O.
50-50 cis trans or 50-50 addition of the H and the BR. Well, okay, so how many chiral carbons do we have in this molecule? In this final product, we have 1 chiral carbon, right? So can I make, first of all, how many stereoisomers are there going to be in this product with just 1 chiral center? Just 2, and those 2 are going to be enantiomers. So do I have any way to make one enantiomer over another? No. Not unless I use a chiral reagent. I don't have any here. So in this case, the stereochemistry of the product is not important. Because I'm going to make them both. I'm going to make both enantiomers. Now I could have let's see, could I have modified this and said, well, here's the problem with the ring. The problem with the ring is I can't fit a triple bond inside of it, so I can't do that with a ring where I could ask you about stereochemistry. But I could say, you know, how do you go from here to could say, how do you go from there to there? What reagent would you use? What same thing? What same reagents? This is a double bond, so you only get one reagent. You'd add Br2. How did you figure that out? Because I added 2 Brs to the double bond, and so I need to know what reagent adds 2 Brs. Was there any particular regio selectivity that we had to worry about? No. Because Br2 always adds 100% trans. So if I would have given you 2 Brs that were cis, it'd be a little more difficult. And let's see, after tomorrow we might know how to do that. But we don't know how to do that today. But it's going to take more than one step. So that's what we do. So what you do here is you've got to figure out, okay, what am I adding, and then figure out the sequence of reagents to add there. You could have also said, let me take my triple bond and decide that I'm going to add my, let me add my Br2s first, so that I would end up with, let's see, if I add 2 Brs to this triple bond, how are the Brs going to add? 100% trans. Then what? Now I've added my 2 Brs, now let's add my 2 H's. So what would I use there? H2 and, like palladium. So that would have given me my, that would have given me the same molecule. And what if I wanted to add hydrogen first? Will this reaction work in reverse? So in other words, if I add H2 here with palladium and then Br2, will that work? No? Why not? Yeah, it's not so much that the H is in excess, it's that we've got a full-blown palladium in there. So the palladium will reduce it down to an alkane, some of it down to an alkane. So I can't use the hydrogen gas and palladium. I can't reverse this reaction. Instead, I've got to substitute that with, I could substitute with hydrogen and Lindlar, or I could use Na and NH3. but I just can't reverse the H2 palladium. So there's 4 ways to solve this problem. And what's my point with this? You've got to know the reagents and what products they get, but you also have to remember what reagent that I need to use in order to accomplish that transformation. So you got to know that for all the addition reactions of the alkynes. The 2 sets that are different from everything else, well, the three things that are different are oxidative cleavage, because you only get 2 carboxylic acids. Reduction is different because I've got 3 methods to reduce. And number 3 that's different is when you add H plus H2O, or when you do anti-Markovnikov, you get a ketone. You get a ketone instead of a alcohol. So that's what's different. So that was the rest of chapter whatever. That was the end of chapter 13, I believe. So were there any other questions about alkynes? Okay. Then let's take a break. When we come back, we'll still get into our groups. But when we come back, we'll talk about, I'll ask you if you have any questions about Grignards. If you do, great. If not, we'll do some Grignard problems. Because that was the beginning of chapter, oh actually no, I take that back. There's a whole bunch of review reactions, which I know are going to be fun. So we'll start up at like 27 after. Wait, no, not Grignards. Right, so here's the question. The first thing for alcohols is, well, here's what we do with functional groups. The first thing we do is we could talk about naming, we could talk about their physical properties, and then we talk about how you make that functional group, and then how you react that functional group. So usually when we're making that functional group, there are review reactions. So the first thing we have is review reactions. So here are reactions that we could use to convert a functional group, and we only have alkyl halides and alkenes to work with, maybe alkynes. So the question is, what reagent would I use for each one of these? So the first thing I want you to do for a couple of minutes is what reagents do you remember for making alcohols? Or you can just jump right to the problem. The problem being I need to know what reagents I need to use for this, for each one of these. So I will give you four minutes to try and remember to fill in as many of these as you can. And just because you hear an answer from one group doesn't necessarily mean it is correct. There probably could be more than one reagent for some of these. It's an OH. It's an OH that's cis to the hydrogen. Okay, what do we have? Okay, which reagents do we have? Let's go through and let's write down all the reagents that you guys came up with. So Hannah's group, give me a reagent you guys came up with. You don't have to give me the reaction it goes with, just give me a reagent that you guys had. And? Well, just H2O with nothing else? Okay, I'll accept that. We'll go through the groups here. Max's group? Yes, I want any reagent. HgOAC2, water and NaBH4. Okay? Brandon and Kaylee. Just a reagent. Okay, BH3, H2O2. Alright, then who's left? Give me a reagent. You guys. Do you have any reagents that haven't been mentioned? No? Okay. Anybody have any others? H plus H2O. Any others? All right, then let's call this, we'll call these A, B, C, D, and then we have an E. So in your group, you can just hold up one chalkboard. But let's do reaction number 1. What reagent would you use? A, B, C, D, E. You could put multiple letters down if you would like. If multiple letters are okay, what's gonna be number 1? Okay, I got 3 E's and a B. So 3H plus H2O's and a B. Any of those would work. Those are all correct. Okay, so really, because if you're adding the H and the OH, you are adding it Markovnikov. And remember that the mercury acetate water does add Markovnikov. Now it adds the H and the OH 100% trans, but in this case, since there's 2 hydrogens here, trans is okay. So either B or E would work for this. Okay, how about number 2? C's. Okay, is C correct? Yes, because I'm adding the H and the OH. Markovnikov, anti-Markovnikov. Anti-Markovnikov. Now, anti-Markovnikov, there's only one way to do it, but that has to be cis. Okay, so 2 is C. That is correct. 3. What reagents could we use for 3? Three D's and an E. Okay, could be A. I didn't say you were wrong yet, did I? How did I imply it? It is. And A wouldn't be any better. So let's talk about. So when you're going from a bromine to an OH, because it is not out of the realm of possibility that if I asked you for the reagents next week that somebody will put down H plus H2O. I mean, I've only seen that probably hundreds of times. So the question is, why is that not correct? Why would A not be correct? So really it's because what's weak. So we've got a weak nucleophile with a primary halide. Weak nucleophiles can only react with what kinds of species? Carbocations. Can a primary alkyl halide form a carbocation? Not unless it rearranges. And that's not the rearrangement product. So when you're looking at this, though, what I would suggest is, what am I doing in this reaction? I'm replacing an OH with a BR. That's not the word I would use. I am substituting an OH for a BR. And as soon as I use the word substitute, what does that mean? It's either going to be SN1 or SN2. In this case, what mechanism is this going to be? SN2, good. So this is SN2. So D would be the only reagent we could use for that. All right, number 4. Okay. What do we got? Okay. So we got 3 B's and an E. Do you guys feel like I'm implied that you're wrong? Not yet, anyway. Okay, so B is the mercury acetate water. So that reagent adds an H and an OH. Markovnikov, 100% mercury trans. So in this case, what have I added? Because now I put 2 methyl groups here. So I've added my H and my OH. There is no Markovnikov, anti-Markovnikov, because the double bond is symmetrical. But I did add the H and the OH 100% trans. So in order to do that 100% trans, I would have to use B. Now, what about E? What would be the difference between using B and using E? E would be a 50-50 mixture. And so if I gave you a 50-50 mixture, or if I didn't show the stereochemistry, then E would be acceptable. If this was a problem, it would be half credit. Because I wanted to see it trans. If I would put the H and the OH cis, in this case, it would have been which reagent? It would have been C. It would have been hydroboration oxidation. So with H and OH, it's a problem sort of like what we just did with the alkynes going to the 3 different reduction products. I could give you an alkene and say, make this alcohol, make this alcohol, make this alcohol. What reagent would you use? Or I could put the 3 different reagents on there, tell me what the product is with stereochemistry. 5. What would 5 be? And if there's more than one reagent for 5, write all the possible reagents. Okay? 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 Okay, we have A's or D's. All 4 groups, A or D. And in this case, what is the mechanism? What kind of reaction is this? What's the mechanism? SN1. So for the SN1 reaction, I'm replacing a bromine with an OH. What could I use? I could use water now that it's SN1 because a weak nucleophile can react, or I could use hydroxide, either one. The strong would just, it's going to form a carbocation and then react right away. So either A or D. You might say, well, what about E? What's the H plus do? Nothing. So I would avoid E. Because I'll at least, at best case scenario, I will cross out the H plus. Worst case scenario, I'll cross out the H plus and then put minus something there. Not the entire problem, but okay. So there's one last reaction. Because if we're talking about reactions to make OH groups, what would be the product of this reaction? With stereochemistry. So what's the product going to be? And then you can write that on the whiteboard. If you have to go back and remember the chart that we developed yesterday. You might want to take another look at it. Okay. Okay. So, okay, what's the question? What's the question? There's a lot of confusion for. Is it clear for everybody? Okay. So again, for this one, Br2, H2O, what am I adding to the double bond? From our chart yesterday. A Br and an OH. So I'm adding a Br and an OH. How am I adding those? Markovnikov or anti-Markovnikov? Markovnikov, so the Br is going to go on the top or bottom carbon? Bottom carbon, and then the OH is going to go on the top carbon. Okay. So if you're writing the product, what you can do is erase the double bond, and I would erase the bond to the methyl group because I need to put in a boulder-dashed wedge. But the boulder-dashed wedge is going to be governed by the boulder-dashed wedge between the Br and the OH. So now they added Markovnikov. Remember, Br now becomes the H+, it's the E+. So it's going to add to the carbon with the most hydrogens. All right, and how did I add the Br? 100% cis, trans, 50-50. 100% trans because the bromine goes through the triangular intermediate. So that means bromine and the OH would be trans, and it doesn't matter whether you use bold dash, dash bold, as long as they're on opposite sides or opposite wedges. Up here with the OH being bold, the way I drew it, I would write the CH3 being dashed. So that's another sort of alcohol preparation, although bromohydrins are a little more special than that. Next question. This reaction we just did. Regioselective only, stereoselective only, both regio and stereoselective, neither regio or stereoselective. And as you're answering that, you might need to consider the other possible products, which in this case are going to be low or 0%. But are the possible products different products? Okay. Okay. No, just write it down with words. Regio, stereo, both, neither are your words. Stereo's fine. Okay. Don't worry, nobody's going to be shocked. What do we think, Nell and Hannah? You can pass if you'd like, or you could say, I don't quite get it. All right, what's your tentative guess? You can just say it. What are we passing on? What was your tentative guess? Okay. So we've got 2 stereos and 2 boths. So let's take them one at a time. Let's do regio first. So the question for regio is what? If I add the BR and the OH one way and then the other way, do I get 2 different products? So in other words, if I added the BR up here with the methyl group and the OH down here, are those 2 regio selectivity, are they different products? Yes. Did I favor one over the other? Yes, because this reaction is Markovnikov, which means the bromine goes on the carbon with the most hydrogens. So is this reaction regioselective? Yes. So does that make sense? Well, in this case, it's not going to necessarily be completely 100% because it's a secondary carbon versus a tertiary. So it's not like a primary tertiary where it's going to be 100% tertiary. You're probably going to get a little bit of this product, but the major product is going to be the top product. So this is regioselective. Does that make sense? Because if it doesn't make sense, you got to say something. Well, it just has to be Markov. Remember, Markovnikov means 5149 all the way up to 100. So in this case, you're actually gonna have a little bit of this product. It's not going to be exclusive, but exclusive is not part of selective. So as long as it's the major product, that's selective. So this one is regioselective. So that's how we do it. We add the 2 groups one way, add the 2 groups the other way. Did I make 2 different products? If the answer is no, you'd stop. If it's yes, did I select one over the other? Is one of the major products? If the answer is yes, then yes, it's regioselective. If the answer is no because it's 50-50, then it's not regioselective. But one of the things that I would look at is I'd look at this alkene, symmetrical or unsymmetrical. Unsymmetrical, reagent, unsymmetrical, so I have the possibility of being regioselective. If either one of these 2 is symmetrical, no regioselectivity. Now, for stereoselectivity, what do I do? Let's look at the major product. What's my first criteria? How many? Need 2 chiral. I need to make a product with 2 chiral centers. Did I do that? Yes. Second criteria then. 100% cis or trans. In this case, 100% trans, and so this is stereoselective as well. So for stereoselectivity, the first thing is, does the product have two chiral centers? If the answer is yes, is it 100% cis or 100% trans? It doesn't have to be, but in all the reactions we've talked about, it's either 100-0 or it's 50-50. And when is it 50-50? So in other words, the reaction can never be stereoselective if it goes through a carbocation intermediate or a free radical intermediate, both of which are sp2 hybridized intermediates. So it will never be it'll never be stereoselective if it's just 50-50. When will it be 50-50? Cis and trans, when you go through a carbocation or a radical intermediate. If you go through a triangular intermediate, it's just a question of, do I make 2 chiral centers? If I go through a square intermediate, did I make 2 chiral centers? If I go through the pentagon intermediate, did I make 2 chiral centers? And I did put in the Monday, well, let's see, today's Wednesday. I did put in the Tuesday folder a whole series of reactions that you can do. Is it regio, is it stereo, is it both, is it neither? As well as writing the products, because that's one thing you'll have to do on Monday. It's in the Tuesday folder. There's the blank problem set, there's the written answer key, and then there are narrated answer keys in 3 parts. And again, with the narrated answer key, it's a PDF file that if you open it up and it says on the top, you need to put it through LiveScribe. You put it through LiveScribe. Otherwise, if you have the latest Adobe Reader and you download the file and open it up in the reader, it will talk to you. Hence the narrated answer key. And you can go from problem to problem by moving the green dot. And if you're having troubles with it, email me or stop by and we can get it to work. You have to have the latest Adobe on either your Mac or your PC. Otherwise, there's a LiveScribe app or a LiveScribe website you can use, but it came and went really quickly. So some of them might have to be played on the player. So those are our review reactions of making alcohols, although they're not much review, right? They're pretty contemporary. Any questions about that? So that's our synthesis. Oh wait, I forgot one more. What if I want to add 2 OHs? Then there's one more. Or is there one more? So how do we do that one? OSO4. Osmium tetroxide, hydrogen peroxide, we talked about that. I think it was yesterday, wasn't it? And then KMNO4 and base. So that adds 2 OH groups, 100% cis. So here's my question about this reaction. Regio, stereo, both, neither. Okay. Okay, everybody said stereo only. Can't be regio because I'm adding two OHs. So I've got a symmetrical reagent. Stereo, it's 100% cis, so now what do I have to check? Two chiral centers. Did I make two chiral centers in my product? Yes. So this is stereo only. So when you're doing the alkene reactions, one of the issues is, you know, when you're looking at regio and stereo, you have to take each reaction individually. In the problems that I put online, it's very methodical. I'll give you a cyclohexane or cyclohexene. I'll put one methyl group on it. I'll put two methyl groups on it. I'll make a methyl and an ethyl. Could you get different answers for each one of those problems? Yes. So each one you have to take individually. Because one methyl might be one answer, two methyls might be another answer, and a methyl and an ethyl might be another answer. So you have to take it individually. The rules for regio selectivity as well as for stereo selectivity. And maybe we'll do more of those tomorrow as well. But I'm definitely going to ask you that on Monday's exam. All right, so any questions on that other than you probably need practice? The only other topic that we're going to go into and that you're going to read, watch tonight, and we're going to do tomorrow is Grignard reactions. All right. So for Grignards, what I'd like to be able to do is this. I would like to do acyl addition by adding a C-, which is called a carbanion. I would like to add a carbanion to the carbonyl group. So how's the carbanion going to add to the carbonyl? What are the arrows going to look like? There's no kind of involved. It's a delta plus trait. It's a delta plus. I'm big on terminology because the terminology can help you. Terminology is not wishy-washy. It's exact and precise. So then what do I get as my product? I've now added my CH3 to my carbonyl, and I now have an O-. This is a great reaction to do because then it should have a delta minus, which was going to be yesterday. What did we do? We did the exact same thing, except instead of using a CH3 minus, what did we use? We used a C triple bond C minus. We used an alkynyl anion. So this mechanism, because I think then once I have my alkoxide, I'm going to go ahead and add acid to protonate it to make my final alcohol. I think somebody said, would we have to do this mechanism on the exam? And I think I said that would be really swell for you because it's easy. It's just 2 steps. But here's the thing with this mechanism. Anything with a negative charge that's a strong nucleophile is going to do this reaction. So alkynyl anion, yes. Any alkyl group with a negative charge. Any carbanion, yes. An H minus. And if I'm brave, I would ask, where does the H minus come from? And if you went back through your notes, you would find out that the H minus came from a BH4 minus, which had in front of it a sodium. So sodium borohydride is a source of H minus, and that H minus can now add to the carbonyl. So I can basically attack the carbonyl with any C minus or any H minus. My difficulty is I know where H minus comes from. It comes from sodium borohydride. I know where our alkynyl anions come from, right? Because where did an alkynyl anion come from? It came from taking an alkyne and reacting it with NH2 minus. But where does the CH3 minus come from? I can't deprotonate an alkane. An alkane CH bond is exceptionally non-acidic. A C minus is the strongest base I can make in organic in this class. So how do I make that? That's where I have to use the Grignard reaction. And so we have to use an alkyl halide, and we use magnesium metal. And that makes a C minus with an MgX plus, so in other words a magnesium 2 plus, 1 halogen, so that's overall positive 1 charge. That's the counter ion. Or I could actually do this by just using lithium or sodium or potassium, one of the alkali metals. Usually lithium. So that then I make a CH3 minus with a lithium plus. And if you do that, you win the Nobel Prize. Every organic student has to know your name forever, and that's Victor Grignard. And that's what he discovered, although he modified what's called a Barbier reaction. There were people that were kind of on the cusp of this, and then the thing that Grignard did was he chose magnesium. I think Barbier chose like sodium, but he did modify it. Why is this reaction important? Because I form carbon-carbon bonds. Almost every carbon-carbon bond reaction in the late 1800s, early 1900s, everybody that discovered one of those carbon-carbon bond reactions won the Nobel Prize and got their name is perpetually honored in organic books. And some people formed 2 bonds, and that was Diels and Alder. So, I don't know. the organolithium and Grignards we're going to treat the same.
Oh,
Is there a difference? It's beyond the scope of this class. Yes, and right now we're treating those metals as if they're spectator ions, but that's not the case. But that's beyond the scope of this class. And also, sadly for you, I have done research in organolithium chemistry, including my PhD stuff. So if you get me talking about it, you'll never get me to shut up. Okay, then for tomorrow, you're going to read the sections, the appropriate sections, which are going to be Grignard reactions, opening epoxides, and then oxidation of alcohols. So these are all reactions, formations of alcohols. Right? I will take your problems. If you sent them to me, when I assign you problems for the next day, you don't have to send them to me at night. You can, if you want, that's fine. You're going to hold on to that. So if you have your homework problems from yesterday, go ahead and you can put them on the table. And then, yeah, the take-home quiz. The take-home quiz problems.
oh,